Hey everybody, welcome to another homework help video. On today's video, we're going to be doing some of lesson 9.2, transformations of quadratic functions. Ooh-wee. And there's a part 1 and a part 2, so there will be a second video covering part 2. Let's click on part 1 here. This one's got 10 questions. The first, there's some 10 questions seems like a lot, but there's some of these are pretty straightforward and it shouldn't take too much time at all. So follow along and hopefully you get some good information here to help you be successful. All right, let's begin. So the first couple of questions here say the graph of y equals x squared is shown. That you're going to get a lot of that on these. Like this is called a parent function, like x squared with no extra numbers added or subtracted or in front or anywhere else. It's just a basic parabola, just right there, just as it is. They want you to graph x plus 4 squared, so y equals x plus 4 squared. So basically, the difference is they've added 4 not to the outside of x, but kind of together inside a parenthesis. There's two ways you're going to see it. You're either going to see it inside a parenthesis or outside of parentheses. Inside, I'm going to refer to as in there with x, and outside I'm just going to refer to as, outside. There's a difference. If it's inside, the way it affects the graph is it moves it left or right. Like without even graphing it yourself, you should be able to look at this and say, oh, this is going to move it 4 units because the 4, and it's going to move it in a left or right direction because it's inside with x. So that's the key thing you want to remember. Inside with x means left and right shifting, and outside means up and down shifting. Now, the thing is this, left and right is reversed. So it says plus 4, which would make you probably think, ooh, I want to move 4 to the right. However, you move the whole graph 4 units to the left. So without even graphing it myself, I know it's 4 units to the left. Now, if you want to check it and you have like when you're doing your assignment, if you want to graph, x squared, and you want to graph x plus 4 squared, you'll see that the x plus 4, the blue one, the after one, is to the left of the original. And you'll notice the vertex went from 0, 0, and negative 4, 0. Every single item on the graph moves 4 units to the left, but the vertex is a really good place to check like the movement. And that's what we're looking at when we're moving our graphs. Okay, the second one said x squared minus 5. When it's not in the parenthesis, that moves it up and down. So in this case, minus 5 moves it down 5. Yes, up and down moves it just the way you think it would. Negative is down, positive is up. However, when it comes to the inside stuff, it moves it oppositely. I would like to demonstrate this a little bit by showing you x minus h squared plus k. On Desmos, you can add these little sliders here. You'll notice these say 1. I'm going to set it to 0 if I have the power. Wait, can I just type 0? Okay, whoa, that's even easier. Okay, so by default, you don't see zeros. You would just see x squared. This is x squared, right? But what if I had x squared plus 3? Okay, plus 3 moves it up 3. And by plus 3, I mean the outside number is plus 3. So that's what the outside thing does. In fact, I can show you this. Let's see if the outside changes. This is a nice little visual for you here. Down moves it down. The more I move it up, the more it goes up, right? Now this one you got to be a little careful on the h value. So here's what I'm going to do. I'm going to reset this guy just so you can see it in the default position. Now let me start playing this one. You'll notice the positives move it right and the negatives move it left. But wait, didn't I say the opposite of that is true? The negatives move it right and the positives move it left. So why is it not doing what I just suggested a second ago when I was solving my problem? Oh man, I was trying to see if I could stop it at 0. Okay, the reason why positives move it right in this situation is because the default sign is negative. When we see a positive, we're not seeing actually positive 4. We're seeing minus 4. So let's say I put minus 4, right? See how that moved it 4 to the left? Well, when we write out the equation, it would look like plus 4 because it's minus 4. I know that seems a little weird. I'm just trying to explain why negatives move it to the right and positives move it to the left. Because what we see is the aftermath of us plugging in a certain number into this formula up here, but the formula up here contains a negative by default in the inside, which is why the inside stuff is reversed and weird. Just so you know. All right, that was way too much explanation. It's way more simple than that explanation makes it out to be. Simply, you just look at the equation and decide if you need to move it up, down, left, or right, and how much do you move it. So let's do it the smart and quick way. I see a inside, that's a left or right. In this case, negative moves it to the right 2 units. I'll drag it 2, done. X squared plus 5, that's not inside a parenthesis with x, so that's an up and down movement. In this case, positive is up. That's it. That's all it takes to know how these things move. You just need to remember what makes stuff move up and down, no parenthesis, outside the parenthesis. What makes stuff move left and right, inside a parenthesis. H and K values for inside and outside. Okay, now we're putting it all together. So there's 2 things going on here. We got -5 on the inside and +4 on the outside. Well, the -5 on the inside moves it 5 units to the right, because remember, the insides are reversed, so negative means right, positive means left, and then +4 outside of this means I move it up 4. And what am I moving? I'm moving all the points technically, but I was really focusing on the vertex. So I'm starting at 0, 0, and going right 5 and up 4. That's literally it. You're just moving it just a couple units. Simple as that, right? Okay, let's see another one. -4, -5. Man, I'm seeing a lot of 4s and 5s on these. Okay, whatever. -4 means right 4. Remember, opposites. Down 5. Right 4, down 5. So simple, right? I'm going to hit try another just so I can show you one more of these. I know it's the same thing. +1, -2. +1 means left 1 because it's opposite, and -2 means down 2. Ta-da! Okay, now here's the thing. If you're thinking about trying to use like Desmos or a graphing device to help you, it's possible a little bit. Okay, if you can actually type it in, unlike me. See how the graph I made on my assignment is very similar to what I made on the picture here, but there's all these dots that appear, and I don't want you to get confused about like what all these dots mean. What you're looking for is the vertex, 0, 0, and the new vertex, -1, -2. Left 1, down 2. It's easier just to know how it moves, right? Okay. Now, this one is a little bit different. This one says graph this, but they're not giving us something to start with and saying move it over. Now, using that same logic we just had a second ago, we would know that normally 0, 0 is a point. And based on what we just learned, -2, -4 means you go right 2, because the -2 is opposite, and then down 4, and that's going to be the new vertex. So at least that's a starting point. Like that gives you a starting point, but how does it grow from there? You can't just click wherever. Like here, is this how a parabola looks? And then I hit a little, yikes. No, it don't work like that. So you can't just put 2 points to each side and call it a day. You have to know, they have to be in specific locations that actually align with the graph. So I'm going to show you something real quick. I'm going to hide this problem. I'm going to graph x squared and show you where points typically tend to go as they move away from the vertex on a quadratic function. So on a regular quadratic function, the vertex is at 0, 0. Not news to us. I'm going to zoom my graph just a bit here. Hopefully this is, okay, this is good. Now on these graphs, let me convert this to a table. Here's the basic 5 points. This is what we're going to make on all of our graphs, but they're not going to be these 5 points every time because our vertex isn't always going to be in the middle. But I do want you to see this. The first point to the right is up 1 and over 1, and the second point is over 2 and up 4. Now, there's a little bit of mathematical reason for why it goes up 1 and over 1, and then up 4 and over 2. Because think about it, you're squaring. If you plug in 1, 1 squared is 1. So if you were to go up, if you were to plug in 1, which is to go over 1, your graph would increase by 1. If you were to plug in 2, 2 squared is 4, which is why you go over 2 and up 4. So what I'm saying is when you're making a parabola, the very default and basic thing to do is to go over 1 and up 1, over 2 and up 4. And that applies to everything. Let me show you what we got going on here with this current problem. So I went over 2 and down 4. And what I'm saying is, from that point, I can go up 1 and over 1. Over 1 and up 1, let's call it that. Let's call it what we see it. Right 1 and up 1, right 2 and up 4. There. Now, I've only made half the graph. You have to copy that, like, how do I say it? Mirror it on the other side. So I go up 1 and left 1, left 2 and up 4, and it matches now. All right. So I'm trying to show you how to make, if you see something in vertex form, the first thing is this. This is vertex form, as you would have learned in the lesson. And it should be very quick to find where the vertex is based on these inside and outside numbers. You wouldn't get that from other kinds of problems. Like, for example, I'm just going to write this to show you kind of how this problem looks not in vertex form. Like if I wrote this problem in not vertex form, I believe it would look like this. X squared minus 4x. See how it has the same point we started at right here? Does that tell you the vertex? Not so good. Or what if you're let me just throw in a random problem. Negative 5x plus 6. Something like that. Okay, where's the vertex at? 0.25. That's not even part of the equation at all, right? But if it was in vertex form, it would be a lot easier to see. This problem would look a little gross in vertex form. I'm not going to lie to you. What was this vertex? X minus 2.5 to the seconds minus 0.25. I'm converting it to vertex form just to show you. Hey, look, I made that same graph I had a second ago on accident. Yeah, this tells you the vertex, see? Without even looking at the graph, I can be like, oh, vertex is over 2.5 and down 0.25. I know that's not a very good problem, but I'm just saying that's a thing that exists, right? Okay, so what I'm trying to get at here is this. If it's in vertex form, you should be able to find a vertex, and from there, there's two very basic directions to go to get the next point. So let me show you that on the next problem, okay? Hopefully there's two of them in a row. Yes, okay, another one. So what I'm saying here is on this problem, I'd look at it and I'd say to myself, okay, this is left 5, down 2. Left 5, down 2. And then, from there, now that you know the vertex, you go over 1 and up 1, over 2, and up 4. And those are the basic points. Now, okay, now I'll mirror those. So left and up, left 2 and up, and it's graphed, just like that. So all I need to do is find the vertex and then know where the 2 points go after that. So over and up 1, over 2, and up 4, because that works in all problems. I'll show you one more time on the next one. My explanation part sounds so long to me, and then I show you like the fast mode, and I feel bad because like how fast it was. Okay, we'll do it fast. Over 3 to the right, up 4, and then from there we're going over 1, up 1, over 2, up 4, and then I'm mirroring those on the left side, and there's a graph, and I check the graph. Voila. Now, if you're absolutely lost and you're like, how are you figuring these 2 points out, or I'm not going to remember that, you're still welcome to make a graph about it. And on Desmos, it'll show you the vertex. How very convenient, Desmos. And just like we did on 9.1 assignment, you can convert it to a table, and the table will contain points. However, just like the 9.1 assignment, some of the points are not necessary. Like this always gives us these 5 numbers, -2, -1, 0, 1, 2. Those aren't what I want. The vertex was at 3, so I should really start by, I should first delete all this. Who needs all this? I should type in 3, 2, 1. That gives me the points to the left, and 3, 4, 5. That gives me the points to the right. Those are the points I just clicked on my graph. I just think it's easier to remember over and up 1, over 2, up 4. I don't know, that's just my opinion. All right, we're going to switch it up a little bit. The next problem refers to the numbers in front. Actually, every problem we saw so far didn't have any number in front of x. So, like, here's x squared. Well, what happens if I put a number in front of it, like a? What is changing the number that's multiplying, not being added or subtracted? What does doing a multiplied number do? Well, if I make it bigger, it skinnifies the graph. Because if you can imagine what's happening is, it's hard to show visually, but imagine something's pulling up on the graph. The bigger the number here, the stronger the pull upwards. So if I put a really big number in front, the graph is being pulled up as much as possible. And now this one's going to be a little bit hard to show you here. But if I go slightly less than 1, see how it pulls downward? It gets squished, gets wider. I'm going to put 0.001. Now to 0.005. See how as it gets really small, it gets very squished. But notice I haven't done any negatives yet. I've done 1 through 10, and now I'm doing numbers that are between 0 and 1. Well, what happens if we go to the negatives? It's the same thing. It flips it upside down, though. So very small negative numbers make it squished upside down, and very large negative numbers still make it skinny, yet upside down. All right, we're going to keep that in mind as we're looking at this next set of problems. So for each coefficient, choose whether it's positive or negative. Okay, easy enough. If it's going up, it's positive. As you could tell from my graphs we just did, negatives go upside down, and positives go right side up or whatever. There you go. You can watch that while we're doing it. Okay, bx squared, that's upside down, so we're going to say that definitely is a negative. Cx squared, that's upside down, so that's a negative. Dx squared, that's positive. All right, now I'm going to pause it for a second here because these next ones are a little tricky. They can be tricky. They're not supposed to be tricky. Choose the coefficient closest to 0. Now, positive, negative, doesn't really matter. The closest to 0 is the widest graph. Like, for example, if I'm showing you on this again, notice this was very skinny as it got further from 0, and as it got close to 0, it did this thing. Hold on, I'm going to play it. Boop. See how it like does that really quick bloop and flips over? Boop. Right as we get close to 0, it gets really wide. And it doesn't matter if it's positive or negative. It just really matters if it's wide. I'm going to make it wider. See? So what we're looking for is the widest graph. Whatever graph is the widest, regardless of whether it's going up or down, that's the closest to 0. So in this case, it looks like C is the widest. So I'm going to say C is the closest to 0. And then it says choose the coefficient with the greatest value. Now, on that case, that's the skinniest graph. But be careful, the greatest value is not just the skinniest graph, it's the skinniest positive graph. Because if you look at this, I'm pretty sure bx squared is very arguably the skinniest graph. It's a little skinnier than dx squared. However, this is not the greatest value. This is actually the least value because it's very, very negative. Like, right, if I put a very negative number, it would be a very skinny upside down graph. But it says what's the greatest value. So the greatest value has to be positive, right? All positives are greater than all negatives. So always look for the greatest value as something that's positive yet skinny. So that's D. We'll do one more just so I can kind of run it back with you here. All right, so positive or negative. Okay, so we've got a negative, negative, positive, positive. Hope that's easy for you. Down, down, up, up. Okay, easy to see. What's the closest to 0? So again, widest graph. Doesn't matter if it's going up or down. The widest looks like B. D looks a little skinnier, so we're going to go B on this one. Okay, which one has the greatest value? So again, that's the skinniest graph that is still positive. C. I want to see one more where it has the least value. Man, they don't have one with the least value. Oh well, we're going to 8. You might get it. All right, the next one now has more to do with these numbers in front. So everything we've been doing on this last problem is some number in front that's causing a graph to go up or down or whatever. But there's 2 ways it can happen. The number in front could be an A value, like ax squared here, or it could be kind of inside with x, which is considered a B value. But if I click the B value and we watch the graph, it does kind of the same thing, right? Wait a second, though. Did you notice the B value never went upside down? Why is that? The reason why the B value doesn't go upside down if it's negative on the inside is because you're squaring it. The squared on the outside is squaring it. So no matter what you plug in, positive or negative, when you square something, it becomes positive, right? A negative times a negative is a positive, and a positive times a positive is a positive. So that's why this one's not flipping upside down like the A value, but it's still doing the same kind of thing where it gets skinnier or wider, right? We're going to keep that in mind when we see some problems. And we can use this to help show like what we're going to get here. So this first thing says use transformations to get negative 2x squared. Now I'm going to show you this. I'm going to type in negative 2 and hit enter. Switch it to my A graph. So it looks as though it's gone upside down. Why did it go upside down? Well, as we learned in the lesson, a negative sign flips it upside down. A 2 would look the same as a negative 2, just, right side up. So first thing is we got to flip the graph upside down. Now, the technical term is reflection over the x-axis because the x-axis is here and the graph flipped over it, right? So we're going to click on the thing that represents that. That's this guy right here. Reflection over the x-axis. Now something else happened. It got a little bit skinnier. If I can show you, how am I going to do this? Let me just put a negative on it. Probably shouldn't be green either. Let's make it blue. Okay. Let's put that here. Okay, so blue is the original graph, except for upside down. And then green's the graph that has -2 instead of just regular old negative. So you'll notice it got a little bit skinnier, right? Technically, it's not skinnier, it got taller, and it got taller 2 times as much. So what happens is we're going to click on this button here, which is the tolerizing button, and they give you a point. Now, this point needs to get taller. By how much? Well, 2. It needs to be twice as tall. Right now it's at -1, which is twice as tall as -1. -2. And if you stretch it as such, it stretches the graph the way that you want it to be. So that's the first graph. Let me run through that again. So negative means I flip it upside down. So they click the reflection button over the x-axis. And then a 2 makes it twice as tall. So I'll click the thing that makes it twice as tall. And it'll go like that. I know it looks skinnier, and you might be really tempted to hit this horizontal thing, which is like the make it squished in sideways button. That's not the one. That's not our jam right there. All right, next one. We got 1/2 to the x squared. So let me turn this guy off, and this one right here. Okay. So here's x squared, my blue one, and we're going for 1/2. So let me type in 1/2. So how does the red graph compare to the blue graph? Blue is normal, the basic thing, and red is when I put 1/2. But you're probably wondering to yourself, wait a second, doesn't 1/2 seem like it'd get smaller in some way? But it looks like it's stretched sideways or got fatter or something. So what happened? Well, here's what happens. When a number is inside the parentheses, remember when we had addition and subtraction inside, it moved it opposite of the way you thought it would? Well, when a fraction is on the inside, it moves it reciprocally as what you think it would. So this isn't really 1/2. This is actually the reciprocal of 1/2, which is 2/1, which is 2. So the graph actually got twice as wide. That's what happened. It did the opposite. So all I have to do in this one is there's no reflections. There's just a twice as wide. So again, it shows me the point, and the current width is 1. That's where the point is. So twice as wide would be 2. Yes, a little tricky there. So if you see something not in a parenthesis, something vertical happened. A vertical reflection or a vertical stretch. That's what it's called, a stretch or a shrink or stretch or compress. Depends on how they call it there. So in this case, it was a vertical reflection and a stretch, 2 times as tall. Here, it was inside the parentheses, so that's a horizontal thing. And it's not half as wide. It's the reciprocal of that, the opposite, twice as wide. We will do more of that. I think the next problem is more of that. Okay, good. All right, so our goal here is can we do this without using any graph help? Like, can you just look at this and know what's up? First of all, I see a negative and a 2, but they're inside the parentheses. So inside always refers to horizontal. So I know two horizontal things are happening. The negative does something, a horizontal reflection. I'm going to click that button. You ready for it? I'm clicking the button. Guaranteed. Promise. It's clicking, and I clicked it. But wait, nothing happened. Why did nothing happen? Well, when you flip this picture horizontally, doesn't it make the same thing again? Now, I don't know if you'll be right or wrong if you don't click it, but just so you know, if you click the horizontal thing, on a basic graph, it will stay the way it is. Okay, what does the 2 do? Again, it's inside, and it does the opposite. So inside means horizontal, so it's a horizontal stretch or a shrink. And is it twice as wide? No, the reciprocal. So this is 2/1 turns into 1/2. Half as wide. Now you got to be a little tricky here. There's 4 little tick marks when you're using Alex. So be careful. This is 1, 2, 3, 4. You want to be like halfway. Make sure it's halfway when you move it, okay? Okay, next problem. We have -1/2 x squared, nothing in a parenthesis. So this is all vertical stuff. So a vertical reflection flips upside down. You should see that. And 1/2 means half as tall. So I'll click this button here and make it half as tall. Now, if you're somebody who's like, ugh, I'm not gonna remember all that, it's okay. You can use graphing calculator, use Desmos to kind of like visualize what you're supposed to be going for. My advice is if you are going to use Desmos, please make sure you graph x squared just so you can see what the starting thing is, and then type in what it is you're going for, you can see what the result should be. Again, you see the negative didn't flip it upside down here, but the -2, the 2 did something. It made it more skinny looking. And technically it wasn't twice as skinny. Well, it's twice as skinny, but it's half as wide because we have to think in terms of the reciprocal. Let's do one more of these. I think 10's a different kind of problem, so I'm going to do one more of 9. So again, 1/2. There's no negative, so I'm not going to do any reflections. And then 1/2 is not inside a parentheses, so this one is a vertical thing. It's half as tall. Vertical things always do what it says. If it's half, it's half. If it's 3, it's 3. If it's, change it to what it is. Here's a -1/2 inside parenthesis. So the negative inside flips it horizontally. Again, nothing visually happens. And then 1/2, you got to do the reciprocal, not half, but 2, because the reciprocal of 1/2 is 2. Twice as wide. Or the graph should look 1/2 as skinny as it was, I guess. I guess that's what we're going for here. There you go. Just so you guys know, there was this arrow button thing, and that's to shift it around. I'm surprised Alex doesn't have these as problems, but any and all of this stuff could happen. Like, we didn't see that yet, but any of those things could have happened. For example, let me just throw out a problem here. -2 x minus 3 squared plus 4. All kinds of stuff has happened. Everything we've done in the assignment so far has happened. The +4 moved it up 4, the vertex. The -3 moved it right 3. You can see the vertex is here. And the -2, the minus flipped it all upside down, and the 2 made it twice as tall vertically as it was before. So all kinds of stuff happened here. And that's the point. That's the whole point of this assignment. Like, you should be able to look at this and be able to describe what you've seen happen. That's what we did on the lesson. I know it went up 4, it went right 3, it did a vertical reflection over the x-axis, and it got twice as tall. It was stretched vertically 2 times as much. All that stuff. It's a lot of stuff. I'm not going to lie. We could have even thrown in like an inside number as well. Inside numbers get a little bit weird because, like, if I put 6 here, it doesn't get 6 times as skinny, I don't think, unless I do that also to the 3. Yeah, because I'd have to make 3 turn into 18. Yeah. So the inside stuff's a little bit weird. If you want to make it 6 times as tall on the inside, actually, it's technically supposed to look like this, which is kind of gross. But yeah, I guess that's a thing. I just bleh. B values are not great, so let's just get out of there before we get too confused. All right, one more problem, and this is like what I just. Oh, wait a second. Wait a second. Oh my gosh, I was just making a problem up, and look what they gave me. Almost the thing I typed. I'm making a -4. There, but again. Here's the deal. You should be able to look at this and say to yourself, oh, okay, I know where the starting point is at least. Over 3 to the right. Remember, it's opposite. And down 4. And there's the vertex. Now, this is where I got to stop, though. Earlier when we did those problems, I said you simply go over and up 1 and over 2 and up 4, right? Well, it doesn't work like that on this one. When there's a number in front, an a value, multiplying to it, everything gets messed up. You still go over 1 and over 2, but the amount you go up is all doubled now. So instead of going over 1 and down, or over 1 and up 1, instead of that, what you'll do is you'll multiply this front value to that instead. Let me show you what I mean. So I'm going to go over 1. You always got to do that. But instead of going up 1, take that 1 and multiply it by -2. So 1 times -2 is -2. Which means I'm going to go down 2. So over 1, down 2. Now, usually I go over 2 and down 4, but down 4 multiply, I'm sorry. Well, we'll call it down 4. Usually I go up 4, I guess. I'm going to go over 2. Instead of moving 4 up, I'm going to multiply that by a -2. 4 times -2 is -8. So from this point over 2, I need to go down 8, which is all the way down at -12. And then I make the mirrored images of that and click it. Now, if you're watching that going, what? Okay, you have 2 choices. Number 1, you can still convert this to a table. Okay, you have to delete the points like we did on the first lesson. We know the vertex was at 3, so let's use 3, 2, 1 to make the left side, and 3, 4, 5 to make the right side. Those are the points I just graphed. I was just trying to kind of describe a way to do it without having to rely on a graphing calculator. So it's still possible. Graph it like that if you want. I'm going to hit try another just so I can show you again. Okay, so on this one, I'm not going to use a graphing calculator here. I'm going to show you. +7 means left 7. +1 outside means up 1. So this inside and outside addition and subtraction told me where the vertex is, right? Now 3 is multiplying out front. So instead of going over 1 and up 1, I'm going to go over 1 and up 3. And instead of going over 2 and up 4, I'm going to multiply 3 by 4 and make 12. So I need to go over 2 and up 12. Which is all the way up to 13 here. Yes, quite skinny, but that is what happens when a 3 multiplies in the front. And boom, I mirror image it, and then I check. Let's do one more. I'll make it fast. This video is going on quite a while here, but whatever, it's good. So left 4, down 1. That's what these adding and subtracting things are. Left 4, down 1. There's my vertex. This is negative, so I know it's going to be upside down. So instead of going over and up, I will go over 1 and down 3. I'll mirror that one right now. Instead of going over 2 and up 4, I'll go over 2 and down 12, because 4 is the usual movement that I'm multiplying by -3. I'm going to go down 12. Oopsies, click the wrong spot. Just get rid of that wrong one. There we go. Again, if that's confusing, like how do I develop those new movements instead of over and up, like the normal amounts? How do I get that? You can still rely on a graphing calculator. It's acceptable, I would say, but it would be best if we understood, like, in advance, I guess. Okay, let me review the assignment here. Talk you through what we learned today. All right, so the first few problems had us just doing basic movement, left, right, up, and down. So inside parentheses was left and right. Outside parentheses is up and down. Keep in mind, anything that happens inside the parentheses is kind of reversed. So a +4 really means left 4 units. So we did it on the first few problems. On number 3, we put them together. So we had left and right movement and up and down movement. In this case, -5 meant right 5 and up 4. We did 2 of those. Okay, then on number 5, oh, no, wait. Was there, well, oh, yeah, number 5 was different, yeah. It didn't have us just clicking a graph and shifting it around. We had to literally graph it ourselves. So what I showed you guys is how to find the vertex, just like we've been doing on these other ones, right 2 and down 4. And then like the default movement to make 2 points to each side, over 1, up 1, over 2, and up 4. The reason why is because 1 squared is 1 and 2 squared is 4, and that's why we shift up that many units. That is only applicable if there's no number multiplying up front, as we learned later in the assignment. If there's no number up front, these are the basic ways you move from the vertex to make the follow-up points. Or you could, graph it and make a table out of it. That's fine too. All right, we did a few of those. I think 7 was the next kind we did. Yes. This one we talked about the numbers that were out front, the coefficients. We talked about positives, negatives, what makes them skinny, what makes them wide. Remember, they get wider the closer they are to 0, but once they go into the negative, now they're flipped upside down. But really small negatives make them still also are wide, while really big negatives are skinny and still going downwards. Then we had some problems with us transforming it. So what does a negative outside of a parenthesis do? What does a number outside a parenthesis do? Vertical stuff. What does the number inside a parenthesis do? What if there's a negative inside the parenthesis? That's horizontal stuff. And we put it all together on 10 by graphing it ourselves. So we use the addition and subtraction pieces to move the vertex. And then we use the number multiplying up front to decide how to move. And this was different. It wasn't like over 1 up 1 and over 2 up 4. It was, well, now you got to take the normal amount you would move and multiply it. So instead of going over 1 and then up 1, I go over 1. You always do that. And then multiply that 1 you would have moved by -2, which means instead go down 2. All right, lots of stuff going on there. I mean, it's not meant to be super easy. The good news is if you're struggling figuring out how to create the image, graphing calculator is your friend, okay? It's not going to give you the answer, but it will give you like a guide as to what you're looking for when you're making your graph. You might as well have it open and using it. Like if you have a blank canvas here and you're like, what do I do with any of this? Well, graph it and see how it looks. Maybe that'll help you get an idea of where to start. All right. All right, this video went on for a very long time. I hope you enjoyed that. Lots of help there. I will be back for part 2, and I'll see you then. Bye.